The X chart is a control chart for the number of defective units, very similar to the NP chart. In this lesson, we calculate the control limits using the binomial distribution. And hello again to this lesson, which essentially has two learning objectives. At the end, you should be able to calculate the control limits using the binomial distribution. And you should be able to implement this knowledge in a control chart and interpret it. This lesson is divided into two chapters. In the first chapter, we will use the binomial distribution to calculate the control limits. And in the second, we will enter this limit in the control chart and discuss how it is to be interpreted. This picture shows the relationship between the various characteristics and the control charts used. The different characteristics are shown on the left and the different control charts on the right. The quantitative characteristics, shown on the left, can be divided into two different categories. First, the variable characteristics. These are all characteristics that can be measured. They always have a value and a unit. Examples of this would be the length, hardness, weight, surface roughness, or tensile strength of a component. But we don't want to go into detail about them here. Second, there are the attributive characteristics. Those are all characteristics one can only count. On the right side, we have the different control charts for attributive characteristics with a yellow background. As you can see, there are 6 control charts for attributive characteristics. As already mentioned, this is about the X chart for the number of defective units. Let's start with the calculation of the control limits using the binomial distribution. The diameter of this piston serves as an example. Although this is a variable characteristic, it can also be checked attributively. For example, with the limit snap gauge. The test result is therefore only a statement as to whether the diameter is within the tolerance. So, just a statement of pass or fail, or accepted or rejected. The results of the tests are shown in the table on the right. According to the test plan, a random sample of 500 pieces was tested once a day. The period over which these tests were conducted was 100 days. A total of 50,000 parts were therefore checked. A total of 493 pistons were found whose diameters were either too large or too small. No further differentiation took place. To calculate the limits of a X chart, be it the warning or control limits, you need the probability function of the binomial distribution, where P is the proportion of non-conforming units. So, the probability of finding an out-of-specification piston. N is the sample size. Furthermore, we will need the average number of non-conforming pistons, X bar. The proportion of defective pistons is calculated from the quotient of X bar and the sample size. As can be seen in the evaluation in the middle, the average number of defective pistons per sample, X bar, is 4.93. This was calculated from the total number of defective pistons found, 493, and the sum of the random samples. There is also a proportion of defective pistons of 0.00986, calculated from X bar and a sample size of 500. A p-value of 0.00986 means that approximately 1% of all pistons do not meet the specification. Now we come to the actual calculation of the control limits using the binomial distribution. We do this with MS Excel and the binom.dist function. The number of defective pistons, for which we want to calculate the probability of finding exactly this number in a sample, is entered in the first entry field, number successes. For example, what is the probability that exactly 11 defective pistons are found in a random sample? So, if you expect 11 non-conforming pistons, then enter 11 in the first field, number successes. The trials field here corresponds to the sample size of 500. The probability of success for the third input field was calculated beforehand. The result is still in the table on the left. This is the proportion of defective pistons in a random sample. If you set the cumulative field to false, the individual probability is calculated that exactly x defects will be found. Here, small bi of x with the value of 0.0074 as seen in the table. The probability of finding exactly 11 non-conforming in a sample of 500 parts is 0.74%. If you set the cumulative input field to true, the previous individual probabilities are added up. Here, in the column capital BI, we find the sum of all individual probabilities of x0 up to and including x11. The result is then 0.9953. It is precisely these summed probabilities that we need to calculate the control limits. Let's just create some space and on we go. So, what do we see in this diagram? On the left of the y-axis are the values for x. As a quick reminder, x is the number of defective parts in a sample. The x-axis is for the probability of finding exactly x defective parts in a sample. The blue bars show the binomially distributed individual probabilities. For the calculation of the control limits, a non-interference probability in the process must be specified beforehand. This is usually 99%. This means that there is a 99% probability that no interference in the process will have to be made during ongoing series production. But this probability can also be 99.73%, which corresponds to the Six Sigma range. Since this lesson is aimed at experts, it is assumed at this point that the terms related to probability distributions are known. With the 99% probability of non-interference, 1 minus alpha is 0.99 and alpha is 0.1. For the two-sided probability distribution, alpha half is then 0.005. As we shall see shortly, the discrete distribution of values for the cumulative probabilities will not result in values that are exactly 0.005 or 0.995. Therefore, the following conditions apply to defining the limits. The lower control limit, x lower, is the largest x value that satisfies the following condition. The cumulative probability must be equal to or less than alpha half. For the upper control limit, x upper, the cumulative probability must be equal to or greater than 1 minus alpha half. This is the case for the first time at 11. This will become clearer when we draw the limits in a moment. Again, for the upper control limit. Based on the chosen non-interference probability, we are looking for the x value for which the following condition is met for the first time. The cumulative probability must be equal to or greater than 0.995. If x is 10, the cumulative probability is 0.988. This is smaller than 0.995. With x equal to 11, this is 0.9953, which is for the first time greater than 0.995. The upper control limit is therefore 11 defective parts per sample. There is no lower control limit, x lower, for this example. It is omitted. Now we come to the creation and interpretation of the X chart. In this control chart, the number of defective parts in the sample is plotted on the y-axis. On the x-axis, the number of the sample. In our example, 1 day corresponded to a random sample. The previously calculated upper control limit was drawn at 11. Because of the selected non-interference probability, all values are expected at or below the upper control limit, with a probability of 99%. Only when a value is above this limit, it is considered violated. This is a signal that the process might be out of control. In such a case, the cause must be found and the process readjusted if necessary. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 3 most important key messages. The control limits for the X chart for number of non-conforming units are calculated using the binomial distribution. The non-interference probability in the process is 99%, but can also be 99.73%, which is equal to the 6 sigma range. 1 or more values above the upper control limit is an indication of an out-of-control process, which may then have to be readjusted. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care and see you next time. Bye.